Okay, everyone, we're going to review the rules for Lewis structures. The first rule, and one of the most important rules, is that hydrogen, we'll do blue, hydrogen only wants 2 electrons. This means that it can only be in one bond. You should never have more than one bond coming off of hydrogen. It should always look something like that. Boron only wants 6 electrons. So it should be in 3 bonds. It should look something like this, right, where other atoms are at the ends of these bonds. So never put more than 1 bond with hydrogen, never put more than 3 bonds with boron. Carbon, nitrogen, oxygen, fluorine, and neon can have access to a maximum of 8 electrons. No more, no less. They have to have exactly access to 8 electrons. Elements on the 3rd, 4th, 5th, 6th, or 7th row, which are also the periods, can have access to more than 8 electrons, but require at least 8 electrons, right? So they can have 8 or they can have more. It depends. And then finally, the leftmost atom on the periodic table generally goes in the center of the Lewis structure, excluding hydrogen, right? Even though hydrogen's on the very far side, the far left side of the periodic table, it can't go in the center of any Lewis structures because it can only support one bond, right? You can only have one bond coming off of it. So then let's do some examples then. So let me change this example here. And this one. Okay, so now we're going to do some examples on Lewis structures. So these are the main rules. These rules are going to help guide us. Let's draw some of these. So the first one is PCl3. And the first thing that you always have to do when you're working on a Lewis structure is count the number of valence electrons. And all that means is you look on the periodic table and you count from the left until you get to your atom. So for phosphorus, right, you count 1, 2, 3, 4, 5 spots. So it has 5 electrons plus chlorine. If you count from the left, you go sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine. It's 7. So there are 3 chlorines. 3 times 7 is 21, plus 5 is 26 electrons total. This is the number of electrons that needs to be in our Lewis structure. So Lewis structure must have 26 electrons in it. Remember, in our Lewis structures that we have these things called bonds. We have a single bond, a double bond, and a triple bond, right? This is 2 electrons, this is 4 electrons, this is 6 electrons. You can also have lone pairs of electrons, but let's go ahead and draw this and see. So phosphorus is to the left of chlorine, so we're going to put it in the center. And then we'll just simply put our chlorines around it. Now, the easiest thing you can do, the first step, is to just simply connect everything. Right? Just do it like that. No problem. And then we need to make sure that all atoms have at least 8 electrons, right? So we don't have a carbon, nitrogen, oxygen, fluorine, or neon, but we do have elements on the third period. So they have to have access to at least 8 electrons. So let's give everyone 8 electrons. So for the chlorines, that means lone pairs. And for the phosphorus, that means put a lone pair on it. Fine. So let's count how many electrons we have. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Well, that looks pretty good to me. So we have 26 total electrons. We didn't need to put any double bonds or anything because when we just lone paired everything up, it worked out. It was fine. All right, let's go on to the next one. Here we have PCl4+. So again, if you count from the left, you'll see that phosphorus, you have to count 5 spaces to get to phosphorus. So that means it has 5 electrons that it's contributing to the structure. And you did that from the periodic table. And then we have 4 chlorines. So 4 times the 7 for chlorines, right? If you count from the left over to chlorine, you're going to count 7 spaces. But then we have this thing here, this positive charge. This means PCl4 is a cation. What does it mean to be a cation? It means you've lost electrons. Well, how many electrons did we have to lose to get a positive 1 charge? It means we lost 1 electron, right? That positive charge means that we have to subtract an electron away. So 4 plus 28 is 32 electrons total. So again, we'll put phosphorus in the center. Put our chlorines around it. And now we're going to put our lone pairs so that every atom has at least 8 electrons. The only atoms that don't need 8 electrons are hydrogen and boron. Everything else needs at least 8. These guys need exactly 8 and no more, whereas everything else can have more than 8. And you're like, Mr. Hicks, what do you mean by needs 8? I don't get what you're saying. So let's look at this phosphorus in the center. How many electrons does it have access to? That means you have to look at how many electrons is it connected to. It's connected to this bond, this bond, this bond, and that bond. Each bond has 2 electrons. So this is 2 electrons, 2 electrons, 2 electrons, and 2 electrons. That means that phosphorus has access to, phosphorus has access to all electrons in green highlighted bonds, which means it has access to 2, 4, 6, 8 electrons, right? So I'm going to erase these. I'm going to re-highlight. Okay, so that's what I mean when I say access. Now let's count and let's make sure that everything here has access to exactly 8. So for the chlorines, we've got 2, 4, 6, 8, 2, 4, 6, 8. You can see that everything is going to have the correct number of electrons. Everything does have access to 8 electrons here. Now, the next thing we have to do is we have to make sure that our structure has exactly 32 electrons in it. So we have 2, 4, 6. 6 times 4 chlorines is 24. 26, 28, 30, 32. So it does have the correct number of electrons. Now, if you're wondering where that positive charge comes from, we will talk about that in just a moment. So now we have NH3, which is called ammonia, not ammonium, ammonia. Nitrogen, if you count from the left, you'll see it takes 5 spaces to get there, plus hydrogen, right, which is just 1. There are 3 hydrogens, right, but each hydrogen only brings 1 electron to the party. So this is 8 electrons total. That means that our Lewis structure has to have exactly 8 electrons in it. So we'll do the easiest thing and just combine all the atoms, right? Now, if you'll remember, hydrogen only wants access to 2 electrons. How many electrons does each hydrogen have access to? Exactly 2. Remember, each bond is exactly 2 electrons. Each single bond is exactly 2 electrons, right? According to right there. But then look at the nitrogen. How many electrons does it have access to? The nitrogen only has access to 2, 4, 6 electrons. So we can't add any more bonds to any hydrogens. You can't do anything like that, right? That's wrong. You can't have a hydrogen with more than a single bond. So we have to put a lone pair of electrons on the nitrogen. Now the nitrogen has access to 2, 4, 6, 8 electrons. So everything here has access to the correct number of electrons that it needs. This is the structure for ammonia. Carbon monoxide, if you count for carbon, you'll see you have to count 4 spaces from the left, and oxygen you have to count 6 spaces from the left, which is a grand total of 10 electrons. So if I stick these together, right, the easiest thing to do, and then make sure that each one of them have access to 8 electrons, right, let's see if this works. I should have 10 electrons in my structure. Let's count. 2, 4, 6, 8, 10, 12, 14, right? This doesn't work because it's too many electrons. So let's try again, but this time let's put a double bond there. And then let's put in our lone pairs. Right? Now check, this carbon has access to 2, 4, 6, 8 electrons. That's perfect. That's how many it needs, which means the oxygen also has access to exactly 8 electrons. Remember, carbon, nitrogen, oxygen, fluorine, and neon have to have access to, not a maximum, sorry, to exactly, 8 electrons, no more, no less. So this one's fine, but let's count the total number of electrons. 2, 4, 6, 8, 10, 12. There need to be 10 electrons in the structure though, so this one also doesn't work because it has too many electrons. So instead of a double bond, let's try a triple bond. Now let's make sure each one of them have access to 8 electrons. You'll see that the carbon has access to 2, 4, 6, 8, and so does the oxygen. Now let's count the total number of electrons. So we have 2, 4, 6, 8, 10. So this is going to be the correct structure for carbon monoxide. Perfect. Okay, let's review how to calculate formal charges. So formal charge is calculated by taking the group number of the element and subtracting the number of electrons the element has in its possession, right? And how do you figure out how many electrons something has in its possession? Say, for example, we had something like this. right? If I wanted to figure out the formal charge for oxygen, what I would do is draw a circle around the oxygen, making sure to capture all the lone pairs and to cut in half, bisect any bonds. Now we know that each bond has exactly 2 electrons in it. So you can think about putting 1 electron of each bond inside the circle and 1 outside. The number of electrons that oxygen here has in its possession is the number of electrons inside the circle. So 1, 2, 3, 4, 5, 6, 7. So oxygen has 7 electrons in its possession. That's how you figure out the second part of this little equation. Okay, so let's look here. Let's do formal charge of the nitrogen. So to calculate that, I draw a circle around the nitrogen. Now each one of those bonds has 2 electrons in it, which means that there's only 1 electron for each bond inside my circle. Nitrogen is in the 5th group. We can look on the periodic table, the 5th main group, right? We're not counting any of the transition metals, so you just go like hydrogen, beryllium, boron, carbon, all that. So it's in the 5th group, group 5, and it has 4 electrons in its possession, so it has a formal charge of +1. So we put a little positive charge there. This structure is for NH4+. Because the nitrogen has a positive formal charge, that explains why ammonium, the polyatomic ion, is positively charged. Let's calculate the formal charge for oxygen here. We draw a circle around it. We know each one of these bonds has 2 electrons. There's an electron inside the circle and an electron outside the circle. But inside the circle we have 1, 2, 3, 4, 5 electrons. Oxygen is in the 6th group, and it has 5 electrons. So it also has a +1 formal charge. So we can show that, I'm going to clean this up a little bit. We can show that by just putting a little positive charge next to the oxygen. The formula for this one is H3O+. Because that oxygen has a formal charge of +1, that's why that H3O+ is plus. That's why it's a cation. For this one, let's calculate the formal charge of chlorine. So we draw a circle around chlorine. We count the number of electrons it has in its possession. 1, 2, 3, 4, 5, 6, 7. Right, so it has 7 electrons in its possession. Chlorine is in group 7. So 7 minus 7 is 0. It has a formal charge of 0, which means you don't do anything. You just leave it alone. It's neutral. This is hydrochloric acid, and it is neutral. Let's do carbon monoxide next as our last example. I'm going to make this a little bigger. So let's do the formal charge of carbon and the formal charge of oxygen. So if I draw a circle around the carbon and a circle around the oxygen, carbon is in the 4th group, and it has how many electrons in its possession? 1, 2, 3, 4, 5. So 4 minus 5 is -1. So we have a -1 here. I'm going to erase this circle. For the oxygen, we have 1, 2, 3, 4, 5 electrons in its possession. Oxygen is in the 6th group, right? This is group, this is electron. We said the oxygen has 5 electrons in its possession. So 6 minus 5 is +1. Here, we have a +1. So -1 and +1 added together end up being neutral, which is why when you write carbon monoxide, you write it neutral. But each one of those atoms actually does have a non-zero formal charge. The final thing I will say is that Normally, you can draw different versions of Lewis structures, right? There's multiple ways to draw them correctly sometimes. The best Lewis structure has formal charges closest to 0, right? That's another rule now. So the best Lewis structure is going to have formal charges that are closest to 0.